Hello everyone. In this tutorial video, we'll be dealing with indeterminate structures. So first, I would like to give you a background study so that we'll be on the same page. So I prepared a little PowerPoint that we can just use to be on the same page. So introduction, this is what we'll be looking at. The few topics we'll be looking at to give us a proper context into what we'll be studying. Equilibrium and support reaction. In order for a structure to be in equilibrium, all the forces and couples, including support and reaction, acting on it will balance each other, and there must neither be a resultant force nor a resultant couple acting on the structure. Now, this is the basis of structural analysis, and you can see these six equations here. These are the equations you use to analyze a structure that is in 3D or is in 3 dimension, or you can come here and say in Cartesian XYZ coordinates system. Yet basically what I'm saying is that these are the equations you use to analyze a body in 3D. So we'll be working mainly on 2D. That's summation of forces in the x direction, summation of forces in the y direction, summation of moments in the z direction. External forces and internal forces. Basically, external forces are loads that act on a beam, and these loads they cause reactions. While internal forces basically are forces that keep the body that's beam together. So we're going to be looking at three major types of supports. That's roller support, the hinge support, and fixed support. These are the reactions for roller. These are the reactions for hinge, and the reaction for fixed. Static determinacy, indeterminacy, and instability. For a beam that has supports on two ends, the reactions must not be more than 3. If it's more than 3, that's greater than 3, then it is statically indeterminate externally. Then if the reactions are just equal to 3, then it is determinate externally. Then if it's less than 3, then it's unstable externally. These are some few examples. This is a beam. They are supported at 3 different places, the two ending and at the middle. We have 2 rollers and we have a hinge support, making it 4 reactions. And basically, it's indeterminate to 1 degree. The same thing here, we have 4 reactions, indeterminate to 1 degree. Here we have 6 reactions, indeterminate to 3 degrees. Okay, so this is an indeterminate structure, a frame structure. So I'm going to be using Excel to analyze this structure. If you're using if you want to analyze this manually, there's no problem. It's still the same thing. I'm just only using Excel to make the work easier and faster. So let's get started. First thing first, I'm going to create a table. But before that, I'm going to bring out the supports. I'm going to put it in a table format. So the first support we have is support A, and then make that capital. Okay, we have support A. Then the next support we have is support B, but support B is going to have 2 subsets. So I'm going to join this together. Okay, then support C is going to have 3 subsets. So I'm going to join 3 bars together. Then we have support E. Then we have support D. All right. So under support A, we have just AB. Under support B, we have BA. We have BC. Under support C, we have CB. We have CD, and we have CE, and we have EC, and we have DC. Okay, so These are what we'll be working. These are what we're going to be working with. So the next thing we're going to look for stiffness. So I took my time out here to get some little explanation about this structure that we have here. So support A and support D are hinged. You can also call it pin. So while support E is fixed. For a hinge or pinned support, our stiffness is going to be 3 EI all over L, while for a fixed beam at both ends, our support is going to be 4 EI all over L. So if you look at this particular beam now, look at this particular place, you can see that A is pinned while B is fixed. So we're going to be going with the stiffness of the very first one, which is fixed at one end and hinge is supported at the other end. So to do this, I'm going to open another app to help me make my work easier. So I'm going to be opening Staad. Right. Let me change the view here. Okay. So I'm going to be defining some things. So first thing first is a modulus of elasticity. It is constant, so I'm just going to give it 1. Then I'm going to define what our I is. Our I equals to, let me take this a little bit down so that I don't block the other things. Our I is 600 for our I for AB is 600 inch raised power 4. So I'm going to actually put a subset here. So let's say IAB. Let me take this small letter IAB. So I want to have 600. But if you look at this structure, you see that we have an obvious problem. You can see that we have feet and we have inches. So I think for us to actually make our work easier, where we have feet, we're going to convert it to inches, so that we'll be on the same unit. So we'll continue with 600 inches raised to power 4. Okay, then we have IB, IBC, IBC equals to 400. Okay, let me bring this down also. Then we also have IDC equals to 500. Okay, then we have ICE equals to 400. So ICE and IBC, they are the same thing because it's just a straight beam throughout. All right, so coming back to our stiffness, that's our K. For AB, we'll have 3EI all over L. So that's 3E. Then we have IAB, 3EI. Sorry, yeah. So we have 3EI. Let me put my multiplication here. 3EI. Okay. All over. Sorry, let me take this. Let me go take this a little bit back. Okay. 3EI all over our L. So our L here is 16 feet. So because of our working with inches, we have to convert our 16 feet to inches. So we're going to do that in a moment. So we can see that 1 feet equals to 12 inches. So if we're having 16 feet technically we'll be having 16 times 12 inches. So that will give us coming. Let's go to our standard back. 16 times 12, that will give us 192 inches. So you can just come back here and insert 192. So this is our stiffness factor for KB. All right, so we're going to get our stiffness factors for BC. So stiffness factor for BC, KBC. So you can say that BC is fixed at both ends. So I'm going to be using 4EI over L. So 4 E times I BC okay. Yeah, our length is 24 feet, so 24 times 12. So let me just use calculator to do that. I want everybody to be on the same page with me. 24 times 12, so that will give us 288. So we have 288. All right, so that's our stiffness factor for BC. So we're going to get our stiffness factor for KDC or CD. Same the same thing. So we can see here we have a pin, and here is actually fixed. So we're going to be using 3EI over L. So that will be 3E times IDC. All right, so all over L, which is in 16 feet. So we'll be having 192. Sorry, I'm trying to move this down. Okay, so you'll be having 192. Okay, which is going to give us 7.813. So the last but not the least will be KCE. So KCE will be equal to, C is fixed and E is fixed, so we're having 4E times ICE. Sorry about that. Okay, we have 12 here, so 12 times 12, that will give us 144. Okay, I think that's basic multiplication table, but just to be on the same page with everybody also, I will just do this here so everybody can see this. Okay, all right. So we've gotten our stiffness factors. So the next thing we're going to do now, we're going to get our distribution factors. So our distribution factor for a pin support is 1. So we'll come here and go 1. So for BA, we'll go back to our mass card. So we're going to get our DF. distribution factor for, let's just put D, let me use capital letter D for BA. Okay, so we're going to be using our stiffness factor for BA, or which is AB. Okay, so we'll come here and say KAB all over KAB plus BC KBC. Okay, we have a problem here, so let me just correct that real quick. So we have 0.628 for BA. So we're going to get our distribution factor also for BC. So distribution factor for BC equal to KBC all over KBC plus KAB. So I'm trying to move this down. Alright, so that we have for BC. Then we're going to get our distribution factor also for CB. That's this D CB equals to, so I'm going to use our distribution, our stiffness factor for CB, and our CB is 5.556. So we'll just put that there in. So BC, okay, all over KBC plus, as KBC plus CD or DC, which is in the same thing, okay, plus CE KCE, which will give us 0.227. So let me copy this to make our work faster. Bear with me. Okay, all right, so Control V. So what we'll be changing here, we'll be changing this from CB. We already have, we've gotten our CB already, so next we're getting is CD. So we change it to CD or DC. So we'll come here, DC. Okay, so we have 0.319. So we'll come here also. Let me move this a little bit upward. We're looking for CE. Okay, so CE. We'll change this to CE. Okay, 0.454. All right, so we're going to get for EC. EC is 0 for a fixed support. The distribution factor is 0 and DC will be 1. So let me just include that here so that we'll have everything down. Yes, we can easily reference to. So we have DC. Okay, so this will be equals to 1. Then DEC, this will be equal to 0. All right, so we have our distribution factors. Yeah, so let me just write this here so that we are not lost. D distribution factor. All right. So let me get that up again. So BA is 0.628. 0.628. BC BC is 0.372. 0.372. Then CB is 0.227. 0.227. Then CD, sorry, I think I made a mistake somewhere, so let me quickly check this. BA, yes. BC, yes. CB, yes. CD, okay. Okay, sorry, no mistake. Just my mind. Sorry about that. 0.319. 0.319. CE, 0.454. Then EC is 0. Then DC is 1. All right. So these are our distribution factors. So the next thing we're getting is we'll get our fixed end moments. So we can just simply shorten that to be FEM. Okay. So I got the fixed end moments for this particular situation. Here we have a concentrated force at the middle, just like what we have here, and we have a UDL across this beam. So you can see from here that for this particular situation, we have our P here will be 3. So 3 times L, which is our 192 all over 8. So we can just quickly come here and include that also. So we're not going to name this, we're just going to just do the calculation. So we say 3 times 192 all over 8. So this is what we have, 72. So for those that might not know, or those that might be wondering how we got that, 192 is the length of 16 feet. When we convert that to inches, we'll be having 192. So that's how we got that over there. There's no magic. All right. We have 72 here. Incoming. Something. Okay. Okay. Okay, so I was thinking, instead of us working with kilopounds per inch per inches, let's work with kilopound per feet. So instead of converting this to into 193, let's use 16 instead. So I will just have 6. I think that's easier to work with. So do not fret. Our distribution factor is a ratio. So us converting our I, that's our second moment of initial, to sorry, us converting our feet to inches, while we're getting our stiffness factor will not affect anything because our distribution factor is actually a ratio. So please do not fret, it's still the same thing. So now that we've gotten this, we can just simply come here and put what we have here. We have minus 6. We are taking our counterclockwise as negative, and we're taking our clockwise, that's BA, as positive. So that will be 6. So BC, let's come back here and do some a little bit of calculation. So from here we can see we have WL. So here our W is 0.5. 0.5 times our length, that's 24 square. Okay, all over 12. Okay, so that's 24. So our BC is 24. Okay, let's change it. Let's take our counterclockwise as positive. Um, it's just the way you want to do it. This doesn't really matter. Just I think I feel comfortable doing it this way. Sorry. All right. Okay. What's our CB? Our CB will be minus 24. Then our CD. Okay. We have nothing on our CD, so we're going to skip that. Our CE. Okay. Our CE here we have. Let's come back. We still have the same load. That's 0.5. We're going to change this to 12. So we have 6. Again, I'm taking this to be positive. I'll see here we have 6. Then here we have our AC will be minus 6. Alright, our DC, we have nothing also. So I'm going to leave that. So what we do next is that we're going to balance our joints. Okay. If we're balancing our AB, we have minus this times our fixed moment times our distribution factor. That will give us minus 6. So here we're going to have let me put this in brackets. We're going to have 6, okay, plus 4. We close the bracket times our distribution factor here. So we have this. Then once opening, also we have this. Oh, sorry. I just noticed something, a mistake I made here. So I'm going to correct this real quick. Okay, so this is supposed to be negative. Okay, this is supposed to be negative. Let me try putting that there again. Alright, so that's supposed to be negative. Okay, sorry for that. So this has already changed. Remember this M32 is this. Okay, then we added it with N32. Okay, so we get the total force here, which will give us 24 minus 6 will give us 18. So 18 times our distribution factor, we get 11. Yeah, but for us to balance the joints, it has to be the negative of what we have for our fixed moment. That's a summation of our fixed moment. So that's why I always add negative here. All right. So coming to the other side again, we add our negative to counterbalance our fixed moment, which is 18. So I'm going to do this. Okay. Plus this times this. All right. So that's what we have there. So we're coming to joint C. Okay. Plus okay. So I'm going to times this by distribution factor of CB. So this is going to give us what we have there. So we're going to do the same thing here. This plus this times the factor we have here. This minus this plus this. Okay, so that's what we have for joint C, and for joint E. I think this will also be easy because we just have only just one sub under E. So that's minus what we have here times what we have here, which will give us 0. All right. Okay, so what we're going to do next is that we're going to start sharing. So since this is only this is a fixed sorry, this is a pin joint, so we're going to share what we have here just once. So we're going to share from A to B. So that will give us okay, we have -3. Then we're going to share from B to C, and we're going to share from C to B. So just come here. Then we're going to share from B to C. So right, then we're going to share from C to E. Okay, so remember, if we have a hinge or a simply supported joint, we're going to be sharing it only once when we're using our distribution factor of 1. Then if we have a fixed joint, we're not sharing anything from a fixed joint. We can only share to a fixed joint. So please have that at the back of your mind. And yeah, since we don't have any fixed moments, before I forget, I have to put 0 here. So we know that we have nothing here. Okay, so what we're going to do now, we're going to balance this joint. We're going to balance joint B. So we're going to say equals to minus. Okay, let me put a bracket there first. Okay, this plus this. Okay, all right. So we're going to share joint C. We're going to balance joint C rather. All right, so let's balance it real quick. There's no need for that, so let's just do this times what we have here. Okay, So let me just explain a little bit on this balancing. So I'm going to open my mask card. Okay, I've already done this before, so let me just explain what I did there. So you see, I added everything that was balanced and gave us back positive or plus 3.348. So what we're balancing is this. That was minus 3.348. So when you add this together, it will give you 0. So that's just what balancing is. So since we've already balanced these joints, we're going to share again. We're going to share from joint C to joint E. So let's share from B to C. From B to C. So now I'm going to share from C to B. Alright. So we balance again. Sorry. Okay, as you can see, I made a mistake here. I was supposed to add the negative sign because we're balancing. So, alright. So let me continue. Negative. So summation of all we have balanced supposed to equal to negative of what we have here. So you can do that on your own, and I'm sure that will give you a negative of what we have here. Alright, so I'm going to leave this because we balance this will give us 0. So I'm going to leave it. There's no need for me to write anything there. Or let me just explain what I'm actually saying. So this times 0 give us 0. Yeah, so that's why I didn't bother to put anything here, because I'm going to see give me 0. So now we're going to share from CE to E. So what we have here. Alright. So now we're going to share from BC to CB, or from joint B to joint C. So let's balance again. This value is already very small, but this value is already very small, but I want us to balance it one more time. So when we balance it one more time, then we're going to stop. We're going to stop there. So let's balance again. So this times our distribution factor. Sorry, I forgot to add my minus sign. Remember, we're balancing. Alright, so this minus this times this. Okay, so this minus this times this minus this times this minus this times this. Alright, so we're going to stop here. We're going to stop there since we already have 0.0. But if you don't want to stop here, you can say continue. It will not really affect your value that much because it's already at 0.0. But If you want to continue, there's no problem. So looking at this, we can see this is 0, 0.0, this is 0, 0.00. I have 0, 0.0, 0, 0.0, 0, 0.0. So I want everything to be 0, 0.00. So what we're going to do is that we're going to share again. I'm going to share again to make everything to be uniform. So we have 0, 0.00. Instead of us having 0, 0.0 here, we're having 0, 0.00 here. I don't know if that makes sense to you, but let's make everything uniform. Let's make everything uniform so that we'll have the same decimal place at everything. So let's share it one more time, just one more time. But you could stop here if you want to. It's not to affect the value that much. It should also affect it just a little. It's already 0, 0.0. So let's just share one more time. So we're sharing from B to C and from C to B. Yeah, so we have 0, 0.00 now. So that's much better. But remember, this will not really affect the values that much. So I'm going to share from C to E. Okay, so let's balance this, then we'll stop here now, since we already have what I want. uh and let me just speak on this again a little bit. You stop balancing and sharing when you have 0, 0.0. It means your value is already very small. The difference is already minute. So it's just like you adding 0.01 to 50. Yet your difference from 50 to 0.001 is just very little. Yet it will not really affect your values that much. It's still approximately the same value. Yet so you stop when you have 0.0. But for you to but for you to actually have for your value to have even a great lesser effect on on the values that you want to have, when you add all your total moments, which I'm going to show you in a while shortly, you can take it to 0.00. Yet to have much less effect on your values. So let's continue. Okay, so this is the last time we're balancing. I see here's already a decimal place of 3. Yeah, 0.0000. Like I said, this will not really affect your it's not going to affect your value. Yeah, so we can stop here. We can stop here. We're not going to move any bit further. So okay, so we're stopping here. So what we do next is that you're going to turn this to a table. So you highlight everything you have done. So you come to insert, change this to a table. Okay, you can still drag this a little bit. You can drag this a little bit down. I'm coming. Okay, yes. So I've made an extra space that we can use for our sum. So right down here, you can just come here and add sum. Sorry, let me make everything capital letter. Yes. So what you do here is that, let's start from here. So you write equals to sum. You sum this. Okay, so what you do next is you come here, click this, you come here, and then you drag. So what this actually do is that everything you have, the addition of the rows you have in your column A, it will apply to what you have in B, C, and E and D. All right. So summation of everything here give us this. 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 And summation of everything here give us this. So that's that. Uh, so these are the values you're supposed to get when you have finished your moment distribution on this particular structure. So just to ensure that what we did is correct, I've already analyzed this structure using Staad Pro Connect edition. So I'll show you that shortly. So this is what we have. Okay, this is exactly what we have. 2 kilopounds, we have here 3 kilopounds, then 0.5 kilopounds. So exactly the same thing. So now I'm going to show you the results on this bin. So remember we had 19.92. Let me show you that. So you can see we have 19.92. So I'm going to check 2.3. Remember at a particular joint, the summation of moments have to balance itself out. So if you look at joint B, you can see that we have minus 19.9, and you can see we have 19.9. So this cancels itself out. So if you look at joint C, which I want to show you from here, you can see that we have 19. We have if you look at joint C in this our model example here, you can see that it's actually 2 and 3. So you can see that we have 19.92, which balances what we have at this other side here at 2 here, which is 19.92. So at 3 here we have 23.34. So let's see what we have here. We have 22.3, which is still the same thing. Here we have 22.34. Here we have 22.3. It's still the same thing. Let's look at beam 3.5. We have 15.43. Then at 5 we have 1.49. So let's look at what we have here. So we're looking at CE. You can see that we have 15.57, which is still good, very good. Then if you look at at EC, I see we have 1.49. So here we have 1.21, which is still very close. So this is how you analyze a frame, an indeterminate frame, using moment distribution. So if you have any question, you can let me know in the comment section. I believe this tutorial will be able to help you understand how to use moment distribution to analyze a frame.